Welcome to the module of waves. Waves are the description of oscillatory motion. And with oscillatory motion, we mean the repetitive motion around an equilibrium. And whether this is in a gas, a fluid, a solid, a vacuum, or even in space-time, the mathematical description of waves is usually quite the same, and also the phenomena that occur. So in this case, we will look at the most simple oscillatory motion, which is the harmonic oscillator. But this already describes a lot of the wave phenomena that we will encounter. So first, let us describe the harmonic oscillator. The harmonic oscillator is a mass m suspended on a spring with spring constant k suspended on a fixed ceiling. And with spring, we can think about something like this. A spring has a spring constant that is either low, such as this one, I can extend it easily, or very stiff, such as, for example, the suspension in a car. And now, we can describe the motion of this mass suspended on the spring using two laws. The first one is Newton's second law. That states that the force exerted on a mass of m gives rise to an acceleration a. But secondly, we use Hooke's law, which states that if I extend this spring a little bit with distance x, I get a force proportional to this extension with spring constant k, but in the opposite direction to the extension. Okay, so what happens now if you just hang this mass in gravity along this spring on this suspension? So we can now equilibrate the balance of forces. So on the one hand, we have the gravity pulling on the mass m with m times g as a force. And on the other hand, we have the spring force counteracting this force and pointing in the opposite direction with a force minus k times an unknown extension x equilibrium. So if we equilibrate this, we can find the equilibrium position to be equal to m times g divided by k. And so again, if the spring constant is low, such as this one, the force will have a long extension, but if the spring is very stiff, it will only have a very small extension. But in this case, we're not yet describing oscillatory motion. So what do we have to do to describe that? And we have to pull it further out of equilibrium. So in this case, we still suppose that Hooke's law is still present, and we also only describe now the deviation from this equilibrium. So we're not considering the static effects of the gravity anymore. So then again, we make a balance of forces. So we can find that the force is again m times a, and the opposite force from the spring is minus k times x, and we combine it to what we call a differential equation. This is a little bit different equation than you are used to, because it's not an equation that gives you a fixed number as an answer, but in fact wants to find a function that is an answer to this equation. Because you can see on the one hand, we have a m times the second derivative of a function x of t, and on the right hand side, we have a function minus k times the same function x. And you might say, well, hey, how am I supposed to solve that? That's quite complicated. But what physicists usually do, we think and we just make a clever guess. And the clever guess you can make by just considering the fact that what we need to find is a function that if we differentiate it twice, we get something of the same function back. Now, okay, you can think hard and maybe you don't find the answer directly, but if you now think a little bit more, you can find that there's a function sine or cosine that is a solution to this problem. And in fact, the most general solution, x of t, is a times sinus omega t plus a phase phi. Please try it for yourself, fill it out in this equation, and see that this is a solution. Now, when you do that, you can find values for the unknown parameters a, omega, and phi. So let's first fill it out and then find a solution for omega. So from mathematics, we find that omega is equal to plus or minus square root of spring constant over mass, But of course, we're only looking for physical solutions. So that this means that omega is positive. So omega is plus square root k divided by m. From this we can find the oscillation time. T is 2 pi square root m over k. So from this you can already see that if I have a large mass, I get a long oscillation time. But also, if I have a weak spring, I also get a long oscillation time. Now we have found the value for omega, but what are phi and a? These are not so easily to find. For this, we have to specify the boundary conditions of this problem. And then we can find the most general solution. So let's assume first that we start extending this spring by a distance a from equilibrium, and we release it without giving it any velocity. Then we can find that the distance x at time 0 is a sine phi. But we know that this distance should be equal to the extension a. So we find a sine phi is a. Well, the most simple solution is to take phi equal to pi over 2, 90 degrees, and have capital A being equal to the extension a. So now, for a specific case where specific boundary conditions, we find a solution. Xt is a sine omega t plus pi over 2. This is equal to a cosine omega t. So we have now not only solved this problem maybe for a specific case, but in the most general case itself. This is a solution for time t is 0 to infinity. So let's look a little bit more into the dynamics of this oscillatory motion. So we have the distance is xt is a cosine omega t. But of course we can also look at the speed. The speed is the first derivative to time of this function. And so this is equal to minus a omega sine omega t. And secondly, the acceleration is equal to the second derivative of this function. So this is minus a omega squared cosine omega t. And so we can already see that the acceleration has a kind of the same dependence as the distance traveled itself. A little bit easier to see is just to make a few plots. This is typically what we do. So I coded that in Python for specific parameters. A is 1 meter, k is 1 kilogram per centimeter minus 2, m is 1 kilogram. And on the top you see the oscillatory motion x, the distance traveled by the mass m. In the second row you see the velocity, and there you can see that the velocity is out of phase by 90 degrees with the extension x of t. And this is of course what you know. The velocity is highest when the mass goes through equilibrium. And finally, the acceleration, you can see it's in phase with the distance traveled, but has a minus sign. So again, when the distance is greatest, the acceleration is also greatest, but then of course in the opposite direction because the mass has to reverse its direction. Now this is the general principle of this oscillatory motion. However, usually what we do, we describe this oscillatory motion not in terms of time, but in terms of phase. And essentially phase determines the amount of oscillations that have occurred. So since the cosine and the sine both have an argument that is equal to radians, units of radians, we express the oscillation times in terms of radians. So at time t is 0, we have a phase that is equal to 0 radians. And after one oscillation time, the phase has increased to 2 pi radians. But for any point in time, we can determine the phase itself. So for example, at a half period, we have a phase of pi radians. And at 1.5 times oscillations, we have a phase of 3 pi radians. But usually, since these oscillations take many times, it's quite common to also express things in terms of phase difference. This is essentially the phase difference between 2 points in time of this oscillation. So for example, if we look at the phase difference between one oscillation and halfway through the oscillation, we can just subtract the phases, and this is a phase difference of pi. And essentially, this describes entirely this phase, this wave phenomena. All right, so this brings me to the end of this first section. And in summary, we have solved a differential equation describing the oscillatory motion of a harmonic oscillator. We found the solution to this oscillatory motion. Xt is A cosine omega t. This is a specific solution for one type of boundary condition. And this is typical of a wave phenomena, in this case, in time. But, as we will see, waves will also have a repeated or oscillatory motion not only in time, but also, for example, in space, or even in space-time. And this is the subject for the upcoming sections in this module. Thank you.